Okay, so today we will start this chapter 8. It will talk about finite automata with output. When we start this course, we said that this is the core science of computer science, and our today's computer is also based on the current logic of this machine, of this course. When we talk about our computer, it is not only about input, but it's also about the output. That when you get some input, what should be the output of in the response of that? Okay. So now we saw different mathematical models so far. They all just validate the input, whether it is regular expression, finite automata, um, and then you saw non-deterministic finite automata, then you saw transition graph TG, and then you saw generalized transition graph GTG. All these are used to validate whether this is valid input or this is invalid input. Is this fail? Is this pass? Is this crash? But now we will see another machine, which is another mathematical model, um, which will be used to give the output. Okay. So now if you see that for the letter of words, we have input. For transitions, we have execution of instructions. For the state, we have contents of memory. So far, output was not there. So there are a number of ways you can get the output. Sometimes you want a response line by line, or sometimes you want a response altogether in one shot. So I mean, some like the difference between compiler and the interpreter. So interpreter gives you response line by line. If there is an error, it will not go further, and you need to fix that, and then it will go further. But if you talk about the compiler, so compiler gives you will you can write your whole set of code, and then if there is any error, so it will compile and give you um, analysis of all the errors in one shot and give you online inline response that particular line, particular column, particular row, you might have this error. So you need to fix that. So that's the idea that we need to give the output. Now for the output, we have machine which is called Moore machines. Okay, we need to understand this thing that this machine does not use to define the language. When we say regular expressions, FATG, NFA, GTG, they use to define the language. So Moore machines does not use to define the language. It is simple machine which will give you output. So you will provide one input, it will give you output. Okay. So because it is not used to define the language, so we cannot validate our input by this machine. Means any input you can give to this machine, but you cannot validate that whether this input is valid input or it is invalid input by this machine. That's the reason that we do not have the sense or notion of final states in Moore machine. So how Moore machine will look like, let me show you the next slide, and then you will get more idea, and then I come back to this slide so then you can understand. So you see this here. So this is your Moore machine. So it has states, it has edges, you have the label on that, and then you see that something Q, these are the state name Q0, Q1, Q2, Q3, and something /0/1. This is basically output. If you are at this state, you will get this output. If you are at this state, you will get this output. And how you move from one state to another state, that is basically your label on the edges. You do not have a sense of start state or final state, but you need to mention that at least there must be one state from where you need to start traversing, and this arrow shows that sign that you can start from here. So because we do not have any final state, so there is no rejection or acceptance of or validity of a word. So you pass a word, it will give, the machine will accept that as input, and how you design this machine, that will decide that what should be the output of this machine. Okay. So now let's go back and see the formal definition of Moore machine. So it says that Moore machine, if you have these five things, so then we can say that this is a Moore machine. What are these five things? Moore machine should have finite number of states, and you need to assign all the states with any same letter, and the number should be different, and the number will tell you that this is your start state, and then all these are the remaining states. So Q0, Q1, Q2, dot, dot, dot. So Q0 is designated the start state. So if you so we know that when we have a Moore machine, it has a finite number of states, and the first state or the start state, it can be, it's a tradition that you can write the give the name that state with zero, any letter, Q0, A0, B0, any letter, but assign zero with that. So this will tell you that you should always start from this state, but there is no final state. So now if you have a Moore machine, so all input letters will be defined by a set of summation. So summation will tell you about the input letters. Okay. So what input you give to machine, it should be composed of all the letters, all the alphabets, which is part of summation. So summation says ABC. So if it is ABC, or it can be 120 or 10 or anything XYZ. So it will be composed of that. And here we have notion of output. Output can be represented by this gamma sign, and this is output letters. Okay. So now output is gamma is equal to XYZ of output characters. So there might be chance that your machine have same input letters and same output letters, and there might be chance that your machine has different input letters and different output letters. So you say that if I press 1, machine will type print output as A. If I give input as 0, machine will do something else. If I give output 2, input 2, machine will do something else. Or you can say that if I give input A, machine will produce output A also. So I mean same set of input and output, or it can vary. That's the reason that we have two different sets for that. So both sets can be same, both sets can be different, no problem. Transition table that shows for each state and each input letter which state to go to next. So we have a concept of transition table, exactly the same concept the way you have in FA and uh, NFA and TG. So the same way you have a transition table here. This will tell you that how you move from one state to another state. And then you have an output table that will shows that if you move from this state to this state based on this out input, what should be the output? That is record or tracked in the output table. So if you have these five things, finite set of states, Q0 is a start state, input letters, output letters, transition table, and the output table. So this will be this combination. We can say that this is a Moore machine. Okay. So now let's see in more detail with the example that how Moore machine will look like. Now, if you see this, we are saying if we are saying that our machine has this number of states. So we just read this. It means we have four states: Q0, Q1, Q2, Q3. And if you follow the standard, we can easily understand that the start state is Q0, and our input letter is composed of summation, so A and B. So it means that all your input is possible combination of A and B. It depends what is this language, and accordingly the way you organize these letters A and B. Output will be composed of 0 and 1. It depends on the input, how you associate input with the output, and then the output will be based on all possible combination of 0 and 1. It depends on how you associate input with output with the input. And now we have this transition table, and if you see that it says if you have if you are at Q0 and this is the start state, output by the old state is 0. And once if you have input A, then you will go to Q1. And if you have input B, then you go to Q3. So look at this one. How we draw the Moore machine by this transition table. So Q0 is my start state. We do not write the minus sign in there. We just have a notion of this arrow outside. This will tell us that this is the start state. Beside, if you do not put arrow, that also not a problem because we can recognize by the number Q0 is always be the start state. And then you are saying output is /1. This will be output whenever you reach at this state. So you will get output 1. So means first output, it is at the start state without giving any input, because you always start from the start state. When you start, you are at the start state. You will get one output by default, which is 1. Okay. It can be anything else, but here in this machine, it is 1. And then it says if you have A as input, you will go to state Q1. If you have B as input, you go to state Q3. Okay. And then you are saying that if you are at state Q1, its output will be 0. And if you have A input, it will go to Q3. Q3. And if it is B input, it will stay at the same place as a self loop. So it will be Q1. Look at this one. And the same way you draw other two states and connect the state with the respective states and the edges and the label and all that stuff, so you can put it there. So now once we have this thing, so then we will see that we draw this machine here and how we pass an input and what is the impact of that on the output. So let's say you have this word AB and you wanna pass this word to this Moore machine. So to receive an input, you need to start from Q0. Okay, so you are standing here, and when you stand here, before you get any input, like in our case, our first letter is A, this machine will give you one output, which is 1. Okay, so because this is the default output, it is without giving any input, it is giving you one output. Okay, and then it says B, A, so you receive A as input, it means you go here and output will be 0. Look at this. And then you have B input, stay here, output will be 0. Then you have A input, A will take you to here, output will be 1. And then you have B input, B will take you to here, output will be 0. So our word finish, and we have an output which is 1 0 0 1 0. So this is basically very simple Moore machine. So you provide an input, it will give you output, and you see that our input and output set is different. It might be same. Um, so now there is one discrepancy here, or one feature you can say of this machine, that output will always be one letter more than whatever is the input, because of this thing that the start state is giving you an output without feeding any input. So that's the reason that whenever you have this input, the output of the Moore machine will be +1 of the size of the input. So the first output does not have any impact on your result. So because this is something which we get without any valid input. But it is the part of this machine. So you have to write that in your answer, but it does not have any impact on your final answer. Okay, you can understand when we go in more slides there, you understand that when I say that it does not have any impact on the machine, so what does it mean? So you will better get understanding when I move to the next slide. So any questions so far here, guys? It's pretty straightforward. It is not hard. It's very easy. And if you have any questions, so I can give you answer. Otherwise, we gradually move to the next slide. Now, let's say we have this machine here. Someone already designed this machine for you, and this is a Moore machine. How we know that this is a Moore machine? Because its output will be at the state level. So you see, it has a states and a Q0, Q1, Q2, and Q3, and output is at the state level. So now what this machine is doing, it is counting how many times you encounter this combination A, B in your word. So let's say if you have a word which is a long word and you are interested to find that how many times I count this thing. So another practical example of this machine is that you are performing some job and you want to count how many times I perform this job in the whole set of these tasks. So you can count particular job by designing or altering this machine. So now this machine in this case is just counting A, B. So now you are saying that, okay, I have, so the actual fun is how to design this machine, but this is basically not in our scope at the undergrad level. So we will not learn that how we design this machine, the thinking process of designing any machine in this case, but uh, we will just do the dry run on this machine. So now when we have, let's say we provide this input, this is our word which we provide to this machine, and we want to see that how many times we encounter A, B here. So now you start from the Q naught here because this is a start state, and this will give you, without giving any input, this output 0. Look at this one. Okay, and then you will receive A as input. So this input will take you to this state Q1, and Q1 will give you output 0. So you have this 0 here, and then you will have another A input. This one, this will take you to state Q2, and its output will be 0. And look at this one, we have this 0 here, uh, this 0 here, sorry. And then you will have this B input, and this B input will take you to Q3, and it has output 1. B input, Q3, output 1. And then you have this A input, this will take you back to Q1 and output 0. And then you have B input, this will take you from here to Q0 and output 0. And then you have another B input, this will take you from here to, it will stay here because of a self loop, and output is 0. And then you have A input, it will take you from here back again to Q1, and output is 0. And then again A input, so the same path you are following again, Q2, and output is 0. And then B will take you to again Q3, output is 1. And then B will take you to this one, Q0, and output is 0. So now the way this machine designed, after so here after passing the last input, our word finish, and we can say that what is the output of this machine? Its output is all these things is the output of this machine. Okay, so our job is to count how many times we have 1 in this output, and you see that we have 2 times 1 in this output. So the way this machine designed, it will give you output 1 whenever it encounter this combination AAB. So look at this one. So you have AAB here and you have 1 here. You have AAB here and you have 1 here. So this is whenever you encounter AAB, so this machine will provide you 1 as an output. So end of the day, from your output, if you just write a very simple code to count how many times you have 1 there, and this will tell you that you have this much time, this combination in your output, or you perform this job that much time. So this is a very nice machine. It gives you idea that how we uh, so based on this idea, you can alter this, you can expand that, or use for any other work to count that how many times we are performing this job in particular automation or something. So this is your Moore machine. So any question here? No questions? Okay. Uh, we are good. So now let's go to the next slide. So that's it for the Moore machines. So we're done with the Moore machine. Now we have another machine which is called a Mealy machine. Mealy machine is very close to Moore machine. It is motivated by the Moore machine, but it has a little bit different behavior with respect of the output. Most of the things are same of as in the Moore machine, but only when we talk about the output, it is different. So it says that. So let me show you how this machine look like. So this machine looks like this way. So same thing, letter by letter, states, finite states. Q0 is a start state. Not it is also not defining the language. It is not validating the word or anything. It is just gives you the output. The only difference is in Moore machine, we decide output at the state level. In Mealy machine, we decide output at the edge level. So now instead of having any output here, we have this output here at the with the label of each edges. So this is the thing we have here. And actually this is very nice thing because this way you remove that discrepancy that the number of input is less than number of output. In this case, when you have an input, you will exactly have the same number of output. So we will so the problem which we face in the Moore machine that the output is different, the size of the output is different from the size of the input. It's not here. And now let's see the formal definition of this Mealy machine, and then we can go and check the further detail of this. So a finite set of states Q0, Q1, Q2, where Q0 is designated the start state. It's the same as the Moore machine. It's the same. Input letters will be summation. We have two different sets, one for the input, one for the output, exactly the way in the Moore machine. Here it is a different. A finite set of transitions that indicate for each state and letter of the input alphabet, the state to go to next and character that is output printed. So the output is decided on at the not at the state level but at the edge level. So this is basically the difference between the Moore machine and the Mealy machine. Now if we draw this, so you can see we have this machine here. Uh, let's see if we have this input A, B, 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 B. So how it goes. So you start from here. You will not get any input. You receive first input, which is A, and this will take you to let's say here, and output is 0. You see this output 0, and then you have another input A. It will take you to here, output 1. Okay. And then you have another input A. Another input A will stay here and output 1. You see output 1. And then input B, this one. From here, B will take you to here, output 1, output 1. And another B, this one. So it will take the output here 0 and output is 0. Okay, so this is the thing that you see that we have same number of input and same number of output. So this is basically your Mealy machine. So in Mealy machine, the output string has the same number of characters as the input string has letters. This is Mealy machine. In Moore machine, and Mealy machine does not define the language by accepting or rejecting input string, so it has no final state. I already explained that. That both machines are not used to define the language. They are only here to give you the output. They will not help you to validate the word that this is a valid word which should be belong to this machine or not. It is not the case. That's the reason that it is not doing or performing any validity check. We do not have any final state in our machine. Um, So that's it. So this is your Moore machine. Any question, guys? Okay, no question. So now we see this thing here. This is some Mealy machine. It says that if you have something like this, that from one state to another state, both edges are at the same direction, in the same direction. So here it says that if you provide A as input, it will give you X output. If you provide B as input, it will give you Y output. So you can combine or merge these both edges, and you can write in this way and separate them with comma. It is the same thing. So it means that if you are at Q4, you can reach to Q7 either by providing A as input and then you will get X output, or you provide B as input, you will get Y as output. It is the same thing. So you can merge the edges if you are converting, if you have something like this. Now we see some practical implementation of this machine. This is another Mealy machine. I'm very much sure that you must understand the concept of complement. What is complement? Complement means the reverse of the input. So if you have one, its complement is zero. If you have yes, its complement is no. If you have true, its complement is false. So this is the complement. So whatever the input, the reverse of that. Okay. So now we are saying that we have this. So now we are more interested to find the binary complement. Just provide 1 and 0 and get the complement of that. Okay. So we are saying our input will be based on 0 and 1. Our output will also be based on 0 and 1. Okay. So it means you will never get any output which is A, B, or something like that, because it should be from this set. So now you are saying here, if you have this output 0, you are at the start state, and if you provide 0 input, you will get 1 output. If you provide 1 input, you will get 0 output, and that's it. This will be your complement. Look at this, how nice small machine, and it gives you very nice output of one very mature mathematical concept. So now if you provide this number here 101, it will give you 010. You provide 001010, it will provide you the reverse of that 110101, because this is the way it should work here. And this is a very nice machine which will give you the complement. Okay? It's a binary complement actually. Just dealing with 1 and 0, and that's very nice machine. So you see that by Mealy machine, uh, you can create this design, and later just imagine that you convert this into the hardware, and you will have one functionality in your calculator which is by which can be solved by very simple Mealy machine. Okay, so now if everything is good, so let's go to the next step. Uh, this is another machine which is Mealy machine, and this will be an increment machine. So you provide as input 1, it will say, it will give you output 2. You say 2, it will give you output 3. So you will say 3, it will give you output 4. So this way it will do that. But it has a limitation that it would only deal with maximum 4 bits. So if your output will be exceed with the size of the 4 bit, it will be overflow, and it will not work properly. Okay, so its maximum limit is to deal with 4-bit information. Okay, so the person who designed this machine, he also tell us the mechanism that how we handle this machine. He said that this machine has 3 states. One is a start state, one is just simple a transition state, and one is a carry state. Okay, so these are the respective input and output. It's very carefully thought by that guy who designed this machine, and he said that, let's say you have a word, and which is decimal word 11. It's not 1 1, it's a decimal, it is 11. How you convert 11 into binary? So you are saying that if you are aware that 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So, if you want to say 11, so it means this is root, this is 1. this is 2, this is 4, 8, and how many which bits you want to on to make it 11. So you are interested into on this bit, and this bit, and this way if you see that this will be 11. Okay. So if you are talking about the binary number has a base 2, and this if you turn on these 3 bits, so this will be 11. So now look at this one. We have 11 here. We convert this 11 into binary, which is on, off, right, off, on. So 1 0 1 1. So if you sum 8, 2, and 1, this is 11. And now this guy said that reverse this bit. So we reverse this. So whatever on the right comes on the left, and whatever on the left goes to the right. So we reverse this. So instead of writing 1 0 1 1 by this way, we start writing by this way. So we reverse it. So 1 1 0 1. So we reverse it. And then it says that pass this number to this machine. So we pass from here, we start from here. Okay, I think this way. So we start from here, and if it is 1, it goes to 0. And then you pass another input which is 1, which is 0. And then you pass another input 0, which is 1. 0 and 1. And then you pass another input which is 1, and its output will be 1. So now look at this one. So when we pass this input and we read from the left to the right, so we start feeding from the first letter will be this one, and then this one, and 0, and then 1. We get this thing, okay? And 0 0 1 1. And now because you when you start this, so you reverse this, you need to get back your decimal number back. So we reverse all those operations when what we did to get this thing. So now because we reverse this, so we again reverse this, and when we again reverse this, it will be, so instead of this way, it will be this way. So it will be 1100. Okay. And if you see 1100 here, what does it mean when you say 1100? Let's turn on those bits here, which is 1100. So you are saying turn on this first bit. This is 0 0. And if you count 8 plus 4 is 12. And if you convert this into the again from that binary to decimal, you will get your 12 back. And 12 is the last number because um, no, 15 is the last number. So if maximum you get the 14, and you will get 15, because when all 4 bits are on, and after that you cannot do anything. Yeah, this is maximum you can achieve from this machine. And then after that it will be overflow. So look at this one. If you have all 4 here, so this machine will not work. It will convert into 0 0, and it is gives you an error of overflow. So that's the idea behind that. So this machine, it is working, and it can give you idea about how you uh, create an increment machine by using Mealy machine. So any questions so far? Quinton, are we happy with this? Quinton, are you there? Mason, everything is good?
Yeah, everything's good.
Okay, that's great. Okay, guys, if this is good, let's move to the next step and see that equivalence of machines. So in short, what is going on? We are saying that if you have a Moore machine, you can convert that into Mealy machine. Or if you have a Mealy machine, you can convert that into the Moore machine. So this is so if there is a Moore machine exist, there must exist it's one of its equivalent Mealy machine. And if we have a Mealy machine, there must be one at least one Moore machine exist for that machine. So this is what we are saying. Now let's see the formal definition of that. So we are saying that at MOB, a Moore machine. So if you have a Moore machine, and this is your MO, denote that with MO. and this machine print X in the start state. So then ME be a Mealy machine. So the two machines are equivalent if for every input, whenever the output from Mealy is W, because Mealy will give you exact output, whatever the input. But here I mentioned that the start state of the Moore machine will print X. So then the output from the Moore machine is XW, because X is the first output which you will get from the start state without giving any input. So XW. So W is a word, actual word, which is your word, and the output will be XW. This is what it says. So it says that it is interconvertible. You can easily convert your Moore machine to Mealy and Mealy to Moore. And now let's see how we do that. For every Moore machine, there exists a Mealy machine that is equivalent to it. So by constructive algorithm, let's see how we do that. So now what we're doing, every Moore machine, there exists. So we are converting from Moore to Mealy. So now when you talk about a Moore machine, what does it mean? Output is at the state level, and it is something like this. So you have a machine. This is a partial machine. It has something. I mean, here also, and after that might be, but we just show the partial of that machine. Um, so whenever you have this kind of scenario where your machine is has the input output at the state level, so you want to convert this into the Mealy machine, so delete this output, and all the incoming edges will have the at the label with the label of the incoming edges, only incoming edges. It might have some outgoing edge, so that is the not case. You do not need to write this output to there. That will be the input of this machine if it is a case. So but for this machine, for this state, whatever the input edges, delete this output and write it here. So once you perform this step, so this way, this is one step which you perform, and you can convert your Moore machine into the Mealy machine. Okay? So it will be look like this. So now let's see, we have this machine here, and we see that all of its output will be at the state level. We need to convert this into the Mealy machine. So now if you see that your first state does not have any incoming edge, because this is your start state. That's why its output is irrelevant. So this zero has no importance in the final answer of this machine. But whenever we write the final answer, we must write what is the start state output, because without that answer will be wrong. But its importance is irrelevant. It does not has any impact on the machine. So now we have, so this output we ignore, and now we consider this state. It has one incoming edge A, so I delete this one from here and put it here. Look at this one. I delete this here and put it here, and then I consider this second state here. So its output is 0, and it has three incoming edges, 1, 2, and 3. So I delete this output and put 0 with all these things. Look at this one, 0, 0, and 0. And then I go to this state. It has one output. I delete that. It has 1, 2, and 3 and 4 incoming edges. So A, B, A, B. So I put individual output with A as 1, B as 1, 1, and 1. So that's it. So you perform this job and you successfully convert your Moore machine into the Mealy machine. And we have this observation. uh, we have the same number of states, we have same number of edges, just the output which is at the state level, it will be deleted and it is transferred to the edge level. That's it. And the first state, which is a start state, we just ignore its output, because we don't have any incoming edge actually where we can transfer that. So we simply ignore that, and that's a very simple process of conversion from of Moore machine into the Mealy. Okay, so this is Moore into Mealy. Any questions so far? believe this is very straightforward. And now it is good. Now we will see that how we convert Mealy to Moore. This is a bit technical. I need your attention here, more attention, please. There I can try to discuss all possible scenarios of that, and then we can see how we can do this. So for every Mealy machine, there exists a Moore machine that is equivalent to it. So it says that how we do this, how we convert that, we need to understand the different scenarios of that machine. So might be okay here. I don't want to go with this scenario first. Actually, this is a bit complicated. I want to go this scenario first. Now, if you see this, that might be your Mealy machine will be like this, that it has a state and incoming edges, and all incoming edges have the same output. Okay? If that is the case, so then this is step one. So then you simply delete that output and shift that output to the state level, and that's it. It has the same meaning. If this is a Moore machine, what does it mean? If you come from here or from here or from here, you will get one output. And what does it mean here? If you have A input, give you one output, B input gives you one output, B input gives you one output, and all three inputs will take you to state Q5. It's the same meaning here. So this is your first step. First step is when you have the same output. Okay, so it will be very easy. Second scenario is, let's go back to the previous slide. Look at this one. We have state Q4 and we do not consider the outgoing edges. We do not consider the outgoing edges. We only consider the incoming edges. And incoming edges, we have three incoming edges here. But if you notice that those three incoming edges are not consistent, they have two different kinds of input here, output here. So if you follow A input, it will give you zero output. B input give you zero output, whereas this B input will give you one output. So now in this case, what you need to do, you need to divide this state into two instances. Okay, so let me draw here. So I will say I will divide this state Q4 and its first instance, and it will take care of output 0. And then I divide this state Q4 into second instance, and here it will take care of output 1. Very good. So we divide this state into two substates. The name of the state will be same, output will be different, and we mentioned somehow by writing one or two that this is first instance of this the same state, this is second instance of the same state. Now all incoming edges which have the output 0 will be handled by the state which is taking care of output 0. So it means this one and this one will be drawn here. So A and B. Okay? And that is good. And then all input incoming edges which gives you output 1 will be handled by this state B. But from this state, when this is in this machine, you can go to state A by providing input A, you can go to this one, or by giving input B, you can go to this one. So you need to maintain these both outgoing edges to the both states. So both state will have A slash 1, B slash 1. So B slash 1 and A slash 1. Both states will have. Okay. So because we need to maintain outgoing edges from the both state. But only incoming edges will be those incoming edges that state will handle, which provide the respective output, which will map with the output which is in the state. So that's it. So if you see this exactly, this is what we did. We have Q14, Q24. Outgoing edges are the same. Incoming edges are this, and this. And that's it. This is the first scenario. This is the second scenario of your input machine. Okay. The first scenario is same input, same output. Then no need to split this state. Just write the output in the state level. Second scenario is you have different inputs, and you can do this way. Okay, split the state into two states. Now let's see the third scenario. So now if the third scenario, you need to be very careful how you can handle this. And if you follow the way I will say, it will be very easy piece of cake. Otherwise, it is very hard. People will confuse. My understanding, people always do mistake in the third scenario. Okay. Now, if you see this, we have a state Q3, and Q3 has two inputs. One is A, which gives you output 0. One is B, which gives you output 1. So it is the same thing, the way we deal with the previous slide. But here there is another problem here, that this B is not coming from any other state, but it is a loop here. It's a self loop here. So how you handle the loop when you have these kind of things? So in this case, first we divide, because both inputs are different, both outputs are different. So we have to follow the same method. We need to divide this into two states. We are saying, okay, we have this Q3 first instance handling output 0, another Q3 second instance handling 1. Very good. And now what we will do, we first, to make our life easy, let's say we first handle this thing. So the both states should have outgoing edge with the same input, same output to go to Q6. So we are saying, okay, this is my Q. Okay, let me first draw the state. So Q6, and this is a state, and there is an outgoing edge and outgoing edge to here with A sub 0, A sub 0. Okay, we did this. We split our state into two states. One is handling, now the state which is handling 0, it has that label here, and delete its output edge label from the label, from the edge. And then the loop will be, you have a loop here, and it has B there. Very nice. But you need to connect these two states also. So what is the rule of that? From the non-loop state, move towards the loop state. So it is a non-loop state, moves towards the loop state. And the label will be whatever the label of the loop. That's it. This is the only thing you need to understand. And if you've done that, this is the perfect conversion of your Mealy machine into the Moog machine. So what is the idea? Move from non-loop state to the loop state. The direction will be like that, and the label will be whatever the label of the loop. That's it. And now if you see this, it's our machine is also based on, we convert that, and it is exactly what I just told you. It is like that. Okay. In the next step, then you convert this Q6 also. So delete this 0 0 and put 0 here, and next step you can do that also. Let's say if you are dealing with this kind of scenario of loop, but the input will be same, so then no problem. Then you don't need to split into two, just the same state and something like that, Q3 slash 0, and that's it, and A sub 0 and Q6, in case the output will be same. But if the output is different, so then, and it is a loop or without loop, it has different behavior. Okay, so you need to handle that. So are we good? Okay. No questions? So now let's go to the next step. If there is no entering row arrow, so like you have this Q3 and Q3, there is no entering edge for this one. So how? So then what you do? How you what will be the output of this one, it is 0 or 1. So then it does not. So now just imagine that we are talking about the start state. So start state does not have as any entering. So what will be the output? So it is irrelevant. It is your choice. You want to put 0 or 1. It does not make any difference. If there is no entering arrow, choose any letter from summation output character. It does not matter. You can put here 0 or 1, because the formal process is that you need to put output here, but this output will not be decisive or take part in creation of the word or make any impact on the word. So this will be irrelevant. But you need to write here something, and what value you should write, which is any value from the output set. Okay, so in case now Moore to Mealy, same number of state, but when you convert, and same number of edges, but when you convert Mealy to Moore, it will increase significantly. We will see now one complete example of machine and how we do this, how we convert that into Mealy machine to Moore machine. Okay, so look at this one. So before I move to the example, do you guys have any question? So I can answer your question. Otherwise, I am going to solve this machine. Okay. So now let's see, we have this example here, and it is our Moore Mealy machine, which has the output at the edge level, and we know that Q0 is a start state because of this arrow, and then we know that it has 4 states and all is good. And now we need to convert that. It does not matter from where you start. It does not matter. You can start from anywhere, whatever you feel that this is easy for you, you need to first perform this job, or this is hard for you. So I mean, this is basically your choice. Whatever the way you do, answer and result will be same. Steps might be different if you follow, if you choose one machine, if you choose that how I deal with this machine. I want to do this, or then I choose this state or this state, but the final answer will be same. It will not be different. Okay. Now we are saying that let's consistent with the slide. So what we did. So okay, we start with Q0. So now if you see Q0, Q0 is has this input and this input, incoming edges. So but if you see that it is two different output, it is 0, it is 1, and there is no loop here. So it means that we need to divide this Q0 into two states. One is for the instance 1, one is for the instance 2. One will take care of output 0, one will take care of output 1. We need to maintain all outgoing edges, and then that's it. And now what will be the start state? Again, because output is irrelevant, either you can put arrow here or you can put arrow here. It is your choice. So we it does not matter that from where you start, because both are the same thing. So now based on this, so we follow this thing. And now if you go to the next tab, look at this one. I exactly what I told you. I have this state and this state. This arrow can be this or it can be here. It does not matter. And then we divide this, and we all incoming edges with the output 0 are here, and all incoming edges with output 1 will go here. You will never see A will come into this or B will come into this. You will never see that. And then you maintain all the outgoing edges to both states. Look at this one from here, Q2, Q3, from here, Q2 and Q3. You need to maintain these outgoing edges. Okay, so that's it. So we successfully convert our one state from Mealy to Moore. And now we again see which state is easy. We can choose that. So now I think that Q1. So now okay, here I think we are going in order Q0, Q1, Q2, Q3, like that. But this does not require. You can choose any of the state. It does not matter that which state you choose first. So now we go for Q1. Q1 has two incoming edges, B and A1. Both have the same input, so makes our life very easy. We just delete this one from here, this one from here, and put one here, and that's it. And now if you see this in the next, I just delete the output of that and put it here, and that's it. Okay. Now I believe that it should be Q2. No, now we are doing Q3. Uh, what we are doing now? We done this Q1 and now Q3. Yes, Q3. So now if you see Q3, so you have how many? So this one is incoming and this one is incoming and both have the same output. So it's again very easy. Delete this, and put /0 here, and that's it. So we exactly did this, and look at this one. So Q3 is 0 here. We delete this, and we delete the output from here, and we done this. So we successfully converted Q this state and this state and this state and this state. And now we have this Q2 state. Okay. So Q2 state, if you see that it has multiple incoming edges, this one, this one, this one, self loop is also incoming, and this one. Okay. So now if we see that we have four incoming edges. So this is one output, 0 and 0 here. So it has a loop, it has a different output. So all possible complexity is related with this state. So what this state require us to do, this require us, we need to divide this Q2 into two instances. Q2 0, it will handle 0 output, and then Q2 1, it will handle 1 output. Okay. All incoming edges which has 0 should go here, and which is basically which is basically your B and A. Okay. And all incoming edges with output 1, which is AA, will go to this one. Okay. And beside this is and you need to maintain outgoing edges from both states. So now if you have Q2, it has outgoing edge A, and so the same way it should be connect with this, and it should also connect with this. Okay, so you should maintain outgoing edges with both states. Beside, now you know that it is a loop here, so we need to connect these two states also with each other. And what is the rule? From non-loop state to the loop state, and the label will be whatever the label of the loop. That's it. We follow this thing, and we will successfully implement this machine here. What is this? Q2. Look at this. Q2 is here, and Q2 21 and Q2 10, and and that's it. So look at this one. So from non-loop to the loop state, and the label will be label of the loop, and then all incoming edges with A and A here, and this one is this is a self loop here. Sorry, this is a self loop here, and it should have another label. Here it is. This one, this one. Okay, and that's it. And now this is your final Moore machine. And but if you see that when we start from this machine, so how many states? We have four states, and when we end, we have this much: one, two, three, four, five, six states, and our states are increased. For sure, if state is increased, the number of edges will also increase. So this is the thing that when you convert your Moore machine into Mealy machine, there is no change in the size of the machine. But when you convert your Mealy to Moore, so the size of the Moore machine will change, and it will have more number of states and more number of edges. So that's the idea behind that with the Moore machine and the conversion and the equivalence. If you guys have any question here, please you can ask. Otherwise, I think we are good. So James Evans, are you happy with this?
Yeah, it makes sense to me.
Okay, that's nice. So Nabhan, Aziz, are we good?
Yeah, looks good.
Okay, and there is another. Is Nikhil? I saw him and he left. Oh, yeah, he left. Looks like. Anyways, so we are good with this. And what happened next? Okay, so now here, this is another idea that how we use this gate and convert to the Mealy machine. So you have a circuit board. If you guys have the background of computer engineering and you took this logic design course, you must be well aware that logic design course, what is the NAND gate, what is the delay. So now if we see this machine here, what does it say? It says that Mealy machine describing a circuit. So now we need to convert this circuit diagram into the Mealy machine. We can convert that. Okay, how we do that? So we are saying, so this is, so now I mean, this you need to be very much focused here because it is a long process. If you see here one slide, and so it's just such a long process, you see. So but it's not hard, and we repeat the same job again and again, but you need to understand what's going on. We have this now. First we understand this machine, this circuit, what's going on in this circuit diagram. So you have your input here. You start your input from this side, okay, and then this is also your input. It goes here. So input can be go directly to the OR gate, or it goes to the NAND gate. This is the input here. And once you have this NAND gate, then you have this output goes to as A here. Here you have this state of this. So you want to check that at this state, what is the value of the output? Is it one? Is it zero? Or what's going on? So you are checking the value at the two states. At the one is here and one is here. Okay. So now you are saying that okay, this is these are the two places where I'm checking my output, and then you can come here. Either you go here or you go here. If you go here, it is not changing any output, but it is simple delay. Whatever the A, it will remain the same here, and then it goes here, and from here it will be OR output, or it goes here or and comes here and OR and go back NAND and continue the process. Okay, so that's a simple explanation of this gate. It is doing something. So what are the possibilities? Possibility is, let's say if you have input 1, then might be because it's a binary machine. Yes, it's a circuit. So NAND will give you output might be 1 or might be 0. So it means that A can be either 0 or 1 here. The same way B can be either 0 or 1 here. Okay, so these are the only two possibilities. So A can be might be 0 or 1, B can be might be 0 or 1. So now if you perform permutation of all possible combination of these in output, so we can say that might be at some stage A will be 0 and B will be 0. If that is the case, when your A is 0 and B is 0, we will say this is our state Q0. I mean, it's not related to that 0 0 should be Q0, but you can assign any name to that state. We start from this way, so we assign this to Q0. And then you are saying might be I have still A is 0, but B will become 1. If I have this combination of the states when A will be 0 and the B will be 1, I will say this is state Q1. Q1 will be when your A is 0, B is 0. Look at this one. Or might be at some stage when you have some input, you perform some operation, A will become 1 and B will become 0. When you have this scenario, so then your Q2, that we call that this combination of A and B, well, this combination of the value of A and B, we will say this is Q2, and might be at some stage both are 1. So in this case, we are saying that this is Q3. So we have no idea how we achieve these states, but whenever we have this combination, now we at least assign a certain state name to them. So we know that A00, whenever it happen, we will say this is state Q0, then 01 will be Q1, 10 will be Q2, 1 will be Q3. So we decided this, and because all possibility will be 0 and 1 here. Now we are saying how we decide what is, if you are here at the B, so how you know that what is the, so now initially let's say this is its value is something, it has, so because these are the placeholders, these are the variables, so we perform some input and it has some value here, let's say it is 1. So now move here, and and we come here, we perform some job here you have this one, and this is the A value. How you decide that what is the new value of B? The new value of B will be whatever the value of A, that will be, it will be goes here. Yes. So because it is just a delay, it is not any gate, it is not performing any job, it is just creating a delay. So whatever the value of this A, we can say this is the old value of A, this will be the new value of B. So because of this circuit diagram. So now we write this rule here, that how you find the new value of B by looking at old value of A. How you find the new value of A? So now then this thing. So new value of A will be, who will decide what is the new value of A? Input, NAND, and then you need to see OR operation between old value of A and the or old value of, look at this one coming here, old value of B. So you need to old value of B, old value of A, perform OR operation on this one, and this will be go here, and then this will be NAND with the input and this thing, and this will decide the new value of A. So this is basically your circuit diagram. We read this from the circuit diagram and we write the rules here. So input, NAND, and old or old B. So this is what we write from the circuit diagram. And what will be the output? How you decide what will be the output? Output will be input or old value of B. So this will be out in your output, or old value of B. This will be your output. So we have three things: new A, new B, and output. We can find these by following these rules here, by and how we generate these rules by looking at the circuit diagram, and then we assume that all possible values of A and B, and we assume that it is a circuit diagram. It should be binary value 0 and 1, and we consider all possible instances of A and B. And we assign a certain state name to those instances of different values of A and B, and that cover all possible permutations. And we have the rules here and the transitions, how we generate the new values. So once we've done this one, now we use these transitions and these possibilities of these value of A and B, which will be the state name, and we will see that what are the different scenarios we will evolve. Any question here? What we are doing, we want to convert this circuit diagram into Mealy machine. Questions? Very nice. So now we are saying that, let's go to the next slide. At various discrete pulses of a time clock, input is received, the state changes, and output is generated. So we at different pulses you will get different input. Okay, so might be you will get input 1, might be you will get input 0. So we assume that. Okay, so now we will see that, what if, suppose we are in state, now look at this one. So suppose we are in state Q0 and we receive input 0. Okay, so you are in state Q0 and you receive input 0. Okay, this is what we are saying. So now how you decide what is, because that's it, this you always initiate your circuit diagram. You need to know what is the previous value of A and B and what is the input. That's it. So previous value of A and B is your state, and then you will have input will be only two possibilities, 0. So you need to check that what happen if you have input 0 and this value of A and B. What happen if input is 1 and the same value of A and B. So you consider all those possibilities. Okay. So now we are saying, okay, let's consider first possibility that state is Q0, input is 1. So now so now here Q0 means A is equal to 0, B is equal to 0, and input is equal to 0. So now new B is equal to old A. What is old A? Look at this one, 0. So it will decide the old A. So what is new A? Input NAND old A or old B. We write that rule here. Input is 0. NAND old A is 0. Old B is 0. Apply OR here. This is 0. 0 NAND 0. So this will be 0 because 0 or 0 is 0. And 0 NAND 0 is 1. So it's a NAND gate, yes. So, and then we find this is new A, new B. And the output will be 0. So how you decide the output? Output will be here, input or old B. Okay. So what is input? 0, and old B is 0, and based on that you will have this output. So now once we done, we put the values in the respective transition formulas. We will find the new value of B, new value of A, and the output. So now what is new value of B? New B, this is, you need to understand, new B is equal to 0 and new A is equal to 1. Look at this one, 1. Now, if you have A is equal to 1 and B is equal to 0, what is this state? It is A is equal to 1 and B is equal to 0. Look at this one. It is a state Q2. So it means that if you have this setting of, if you are at state Q0 and you receive input 0, you will go from here to state Q2. Look at this one, state Q2, because we will get this output. And now we will perform the same job staying at the state Q0, but the input, we change the input. Look at this one. So we are saying you are in state Q0, which we were there before, but now we suppose input is changed. Let's say because this is a different pulses you will get. You never predict that you will get the same input. It's a different pulses from the computer. Might be it will be 0, it will be 1. So now you have this state here. So now you are saying if this is a state now, how the same formula, new B is equal to old A. So now A is equal to 0, B is equal to 0, because how we get this? Because you are at state Q0 is 0, new A will be 1, output will be 1. And so now if you have B is 0, A is 1, what is this? It is Q2. So you will be at the Q2. And this way you will find, now you consider if you are at Q1, input 0, put the values in the formula and find the new A and new B and check from the table what is this new A and new B, and assign the state name accordingly. And then so this is Q2, and then if you are in the same Q1 and receive input 1, find the formula, and it will give you based on the new value of A and B. So you will be in the state Q0. Okay, and then you can do this with state Q2 input 0, input 1, and find the respective new states. Q3 input 0, Q3 input 1, find the respective new states based on the new value of A and new value of B. Okay, so this will be Q1, this will be Q3. And then once you've done that, you draw this table here. So you are saying old value of state Q0, you draw the transition table basically. So after input 0, this is a summary table. This is a transition table, what we just did. And after input 1, if you are at Q0 and the new state will be Q2 and output is 0, because we already find what is the output also. Look at this one, output and the new state. So we just summarize that in form of transition table, and this way we figure out what happened if we have one input. And now based on that, once you've done this, so now this is basically your transition table, and you all know that you can easily draw the machine from this transition table. Look at this one, Q0, if you are at here and after input 0, so input is 0, you will go to Q2, and after and output will be 0. Look at this one, complete information we have. And after input 1, you will again go to Q2. Look at this one, and output will be 1. So this way you draw all the connection of this machine, and you successfully convert your circuit diagram into the Mealy machine. And this will be helpful. This shows that, I mean, what when we are saying that this logic is, our computer is based on this logic, and we still using this knowledge to design our current computer, our laptop is i7, whatever these machines, it is a core science, so it will not change, and we use this logic for this thing. And this is the summary of this thing, that so far what we cover. We cover the start state, and it has FA. FA has one start state, and transition graph has no restriction. It may have more than one start state. GTG has no restriction. It may have more than one start state. FA and and non-deterministic, and NFA has also restriction of one start state. The same with the case with Moore and Mealy machine, one start state. And then we are saying that when you are talking about the final state, finite states, FA has no restriction. You may have 0, may have 1, may have more than 1, and that is the case here. And Moore machine and Mealy machine does not define the language, so it have the start state or final states. So here letters of labels on the arrows and all that information. So number of transitions from each state, how you can move from one state to another state. Deterministic, FA is deterministic, TG is not deterministic, non-deterministic, and NFA is also non-deterministic. Moore and Mealy machine is deterministic. Okay. So output, so these things will not give you any output. This will give you output. This is summary of, so far we covered 8 chapters, and this is summary of that. And here I think that we finished this. And I want to mention here that I got some slides of this course from Dr. Amy Felty. She is a distinguished professor of University of Ottawa, Canada. But later I add a lot of material in that, and I use this book, Introduction to Computer Theory, second edition. So this is the main source of the slides. So I have the copyright of that. Anyone who want to use this for any educational purpose, please, you are more than welcome to use this for any educational purpose. You don't need to take permission from me, but I mean, I have copyright of all this stuff. I added a lot of stuff in the original slides, which I got from Dr. Amy Felty, and I'm thankful to Doctor that she provided me. I can start my work. Uh, so guys, we done this. If you have any questions, so please, you are more than free to ask me a question. I think that I should stop here. And we can, if you have any questions, you can ask. I will come to my office hours in the next link, and I can answer your questions there. So here I am, stop the recording.